Brain-Computer Interface by Brianna Williams, Morgan Vandal, and John Spites. Brain-Computer Interface, or BCI, is a new form of communicative technology used by individuals that have neurological impairments that prevent them from using their peripheral nerves or muscles. What is a BCI? BCIs also go by brain-machine interface, neural control interface, mind-machine interface, and direct neural interface. They use technology outside of the body to connect to the brainwaves being transmitted directly from the brain and are able to translate the information. These outer responses can be movements through a robot or transmitted onto a computer screen. The technology works through algorithms learned by the machine, through either non-invasive EEG electrodes or the more invasive surgeries where the device is surgically connected to the brainstem. Electrical signals from the brain's neural impulses can be read. These learned machine algorithms are then able to transmit the neural signals into action that otherwise would not have been possible. BCIs do, however, have limitations. If a neurological limitation was developed from brain damage at a single origin, like a stroke in the motor cortex, then a BCI would not work. This is because the impulses within the impacted part of the brain are not firing like they should. BCIs are meant to act as substitutes for the peripheral nervous system after actions are triggered by the brain. If the central nervous system is not functioning properly, then these signals can never be created. History of BCIs. In 1924, Hans Berger, top left, developed the technology for the electroencephalogram, or EEG. This was the first time neurological activity could be mapped and the brain's neural impulses could be seen. However, it wasn't until the company DARPA got a hold of EEGs in the 1970s that the development of BCIs could begin. DARPA, or the Defense Advanced Research Project Agency, began to develop concepts that would interface the human brain with computers, according to the Journal of Neuroscience Methods. It was after the research with DARPA began that all methods of BCIs, including invasive and non-invasive, were evolved. It was at this time that demonstrations of BCIs began to be seen with animals and humans alike. In 2001, John Donahue, Wright, was accredited with the most successful of these demonstrations. In conjunction with Brown University and cyberkinetics, he was able to develop Neuroport. This technology would allow Donahue to transmit neurological signals to a robotic arm as it moved its fingers and waved on command. Further, this technology would also be used to identify micro-seizures in epileptic patients that could not be identified before.
There are two main categories of BCI. The first is an external cap connected to multiple electrodes similar to an EEG machine that read the electrical signals that make their way through the skull and skin from the brain. The BCI then uses these electrical signals to cause a change in the movement of either a cursor on a computer screen or a mechanical device like a prosthetic hand. This method is less precise and more shaky than the other option of an internal implant. However, it is cheaper, less invasive, and does not require brain surgery to function properly. Machine learning can help smooth out the movement associated with the external device. The biggest weakness of the external BCI is that it only works in one direction. It reads signals from the brain and then sends them to whatever device it is connected to. Internal devices, on the other hand, can be capable of both sending and receiving signals, potentially allowing amputees and paralyzed people to both move and feel again. Currently, the primary focus is just on brain-to-object movement, mainly because the motor cortex, the region of the brain responsible for movement, is so well documented and localized and the equipment needed for sensation is even more complex and expensive than the already costly and complex one-way internal BCI. Not to mention the fact that sensation involves multiple areas of the brain other than the motor cortex, meaning either a much larger or multiple implants are needed to make it function properly. The picture of this slide is an example of a sensory loop that shows a BCI sending information from the brain to the computer and vice versa. As of the making of this video, BCIs in various settings have controlled a computer cursor, several tabletop and video games, various prosthetic appendages, namely hands, arms, and legs, a full-body exosuit, electrical devices that stimulate the nerves past the point of a spinal cord injury, and many others. The primary focus now is on improving the accuracy, smoothness, and articulation of these devices to better mimic real human limbs. Adding and improving the sense of touch of these devices won't be far behind.
Past innovations include using signals acquired from chips implanted in the brain for robotic device control. However, this required medical and surgical expertise to correctly install and operate these implants, which have limited their use to a few clinical cases. Researchers from Carnegie Mellon University, in collaboration with the University of Minnesota, have made a breakthrough in addressing this problem by developing a non-invasive robotic device control system that continuously tracks and follows a computer cursor. BCI technology sends and receives signals between the brain and an external device. By using electroencephalograms, or EEGs, researchers were able to non-invasively acquire signals deep within the brain and achieve the neural control of a robotic arm. The technology has successfully been tested on 68 subjects. Previous non-invasive human-controlled robotic arms often resulted in erratic motions. However, this new system allowed the arm to follow the cursor in a continuous path, enhancing accurate tracking by over 500%. The non-invasive control of robotic devices using only thoughts will have wide applications with great benefits for patients with movement disorders. More and more researchers are moving towards non-invasive methods of utilizing BCIs. Researchers have designed a, quote, surrogate anthropomorphic robot, end quote, that allows a human operator to bind with it, see what it sees, and replicate the exact movements of a human hand inside a sensor-filled glove. The robot can be used for remotely handling toxic substances, explosives, perform complex surgery, work on the moon, or in search and rescue operations. Another project called BrainAble, being worked on by AbilityNet, is being developed to assist people with extreme disabilities and locked-in syndrome. The computer will be operated using eye movements to communicate. Even though a BCI needs no such voluntary movements of muscle, they also work using thoughts alone. The BCI is expected to be developed in a way where everything will be connected by default. If your brain and nervous system get connected onto the net, then they are automatically a part of a system working together with the computer. You basically become your own cloud. So our discussion questions are: how do we keep a device that is connected to our brain and sending and receiving wireless signals safe from hackers? And what are some ethical concerns involved with brain-computer interface, specifically in regards to autonomy and safety? Thank you.